Bismillah, we start today's class in Business Math 1105 at Sultan Qaboos University. My dear students, we're going to start from chapter 13. And my start today in chapter 13 will be from the very beginning of the chapter. I'll be discussing the following points: intervals on which the function is increasing, and intervals on which the function is decreasing. Okay, so this will be our beginning. Also, we will see a definition of critical values of a given function. This will be our goal also in this part, in this video. And finally, we will be talking about relative extrema, meaning relative maximum, relative minimum of a given function. To start with, I'll sketch a graph of any function f of x, y, and let's have a look at this function. This is the x-axis, this is the y-axis, and here I have y equals f of x. Let me take a point, let's say x1. This a point having on the curve, it has x1 as an x coordinate, and it has f of x1 as a y coordinate. And let's take another one, x2, f of x2. When we come to compare x2 to x1, we find that x2 is greater than x1. What about the function? We have f of x2 is less than f of x1. This is a decreasing curve. On this curve, whenever we take a tangent line to any point, we find that the slope is always negative. So when we say a slope is negative, means on the interval that we have f prime of x is less than 0 in this interval. This is where we call the function is decreasing on that interval. In the same manners, we'll discuss a function which is increasing. Let's have a look here. This is, again, the x-axis. This is the y-axis. And here we have y equals f of x. I take a first point. Let's say this is x1 with f of x1 as a y coordinate, and another x2 with f of x2 as a y coordinate. We compare again x2 to x1. We find that x2 is greater than x1, and also f of x2 is greater than f of x1. This is an increasing function, as we see from the curve. If we repeat the same idea of taking the tangent line to any point, we find that the slope of this tangent line is always positive, telling us that f prime of x on this interval is greater than 0. So whenever we have the first derivative greater than 0 on a certain interval, we can say that the function f of x is increasing. So that's interesting. Now we got the two definitions for increasing and decreasing functions individually, and we move forward to the second thing, which whenever we say about a value x is a critical value, x has to satisfy a certain condition. X equal to c is called critical value. First of all, this c has to be in the domain of the function. If it is in the domain of the function, it's a critical value if it makes f prime 0, or if it makes f prime undefined. Only if it is in the domain of the function, I can call it a critical value. Okay? Now, let's take this and go to solve an example, and I will call this page 1. Example we have in the textbook, y equals f of x equals x plus 4 over x plus 1. First of all, we need to know, before we do anything, we need to know the domain of this function. We see that this function is defined everywhere except at a certain value of x, which is the value which makes the denominator 0. So the domain is all real numbers x, such that x is not equal to minus 1. This is our domain for the function. Next, in order to find the intervals for which the function f of x is increasing and decreasing, we need to differentiate. Some of you would like to rewrite the function f of x again. We say x plus 4 into x plus 1 all power minus 1 to make it easier for differentiation. So now let's go and find the first derivative of f prime, of f of x, f prime equals the derivative of x is 1 plus the derivative of this part, it is 4 multiplied by minus 1 multiplied by x plus 1. Minus 1 is minus 2 times the derivative of inside, which is 1. Here we applied the chain rule. So now we can have f prime of x equals 1 minus 4 over x plus 1 all squared. Why don't we have the same denominator here? So here I have x plus 1 all squared, x plus 1 all squared minus 4. Can we all see that we're having a difference between two squares? Yes. So I have x plus 1 all squared, and up here I have a difference between two squares. The first is x plus 1 minus 2. This is the first bracket. The second one is x plus 1 plus 2. So this is equal to x minus 1 multiplied by x plus 3 all over x plus 1 all squared. Now we need to find the values for x for which f prime equals 0. What is x? And the values of x for which f prime is undefined. We decide on these values of x, if they are critical or values or not, if they are in the domain of the function. So now I have f prime in the form of a fraction. Whenever you have a fraction equal to 0, the 0 is always coming from the numerator. So f prime of x equals 0. This implies that the fraction x minus 1, x plus 3 over x plus 1 all squared equals 0. This implies that we are having either x equals 1 or x equals minus 3. So these two values, is this in the domain of the function? Yes, this is in the domain of the function. Does this belong to the domain of the function? Yes, this belongs to the domain of f, where we have at the very beginning, domain of f is everything except minus 1. Now, we have two critical values. What about the value x, which is equal to minus 1? Note that x equals minus 1 is not in the domain of f, but the f prime of x or of minus 1 is undefined. So can I say that this is a critical value? No. It's not a critical value. X equals minus 1 is not a critical value. Now we take everything to the real line. And I mean by everything, this x equals to 1, this x equals to minus 3, and also the x which is equal to minus 1, and I put them on the real line. I have minus 3, minus 1, and 1. Okay? We see that minus 3, minus 1, and 1, as I put them on the real line, it splits the real line into 4 intervals. Look at these intervals with me. This is the first interval, this is the second interval, this is the third interval, and this is the fourth interval. And on each of these intervals, we want to study the sign of the first derivative. So I take the first derivative, which I found here. This is our first derivative. Come back and look at f prime of x. I'll take it and I go to the real line. First of all, we see the denominator of f prime of x. Isn't it positive? Yes, it is positive. So on each of these intervals, I'm sure that I have a positive denominator because it's something squared. Anything squared is always positive. So, and up there we have two brackets. All what I care for is the sign, okay, of f prime. So let's take any test value to the left of -3, anything which is less than -3. Can you say, for instance, -4? Yes. -5? Yes. -500? Yes. And I go to the f prime. -4 -1, -5 -1, -500 -1, everything is minus. -4 plus 3, -5 plus 3, or even -500 plus 3 again is minus. Minus times minus tells us that everything here is positive. So on this interval, the first derivative is greater than 0. Tells us that this function is increasing or decreasing. Yes, first derivative, the function is increasing on this interval. Now we go further and take a point between -3 and -1. Let's say -2, and we substitute in the first derivative. -2 minus 1 is minus. -2 plus 3 is positive. Minus time is positive over positive, so the whole thing is minus, so everything is, the first derivative here is negative, so f prime is less than 0. Whenever we have the first derivative of an interval negative, of a function on an interval negative, we say that this function is decreasing. Now we go further. Anything between -1 and 1, we should choose the simplest, which is 0. I take 0 and I substitute in the f prime. 0 minus 1 is minus. 0 plus 3 is plus. So the whole thing is still negative, telling us that f prime is less than 0 here also. So this is decreasing here, the function. Now, to the right of 1, anything greater than 1, what value should we choose? 2, 3, 300, again. 2 minus 1, 3 minus 1, 300 minus 1 will always be positive. 2 plus 3, 3 plus 3, 300 plus 3 is always positive. So the first derivative is positive here on this interval. So we can say that the function is increasing. Now, we were asked to find the intervals on which the function f is increasing or decreasing. We can see that from -∞ up to -3, the function is increasing. And from 1 to infinity, or from 1 to infinity, the function is also increasing. And we put a union. So on this interval, the union of two intervals, f of x is increasing. Next, between -3 and 1, we always have the function, the first derivative less than 0, the function is decreasing. So we say from -3 up to -1, union -1 to 1, on this interval, f of x is decreasing. Why did I make a union and I'm removing the -1? Because we know that -1 is something at which, is some value at which the function is undefined. Finally, after we found the intervals on which the function is increasing or decreasing, and we found also the critical values, okay, next we need to find the relative extrema. We can see that the function is increasing on this interval and reaches some value at -3, and then it starts to decrease. So increasing and then decreasing tells us that it reached a maximum. So at x equals minus 3, f has a relative maximum. So f has a relative maximum. F maximum equals f of minus 3. Direct substitution in the original function of minus 3, you will have minus 3 plus 4 over minus 3 plus 1, you will get minus 5. Now, what's happening next? At x equals 1. We see that before 1, to the left of 1, it is decreasing, and then it starts to increase. So at f equals 1, the function f has a relative minimum. F minimum equals f of 1, which is equal to, I go to the original function up there again, and I replace every x by 1. 1 plus 4 over 1 plus 1, it is 1 plus 2, so this is equal to 3. And that's it for this example. Thank you.